Now let's go back to the actual function. There are two versions of this, as there are two versions of the exponential function. F of x equals log base b of x if b is greater than 1. Well, what does this look like? When you're graphing these, what you should know is the following aside. So this uses some things that we just talked about in the last chapter. And I don't know how up you are on your inverse functions. But if I write log base b of b to the x, who can tell me what that's equal to? Anybody?
X.
It's just equal to x because that's the power that turns b into b to the x. Even though it's a cryptic expression, I know how to read it, I know how to interpret it. Also, what if I did this? This one's a little bit crazier. Does anybody know what that one is?
X.
It's also x, and let's talk about why. These are called cancellation laws. Cancellation law 1, cancellation law 2. This first one is maybe a bit more obvious. For one, the power that turns b into b to the x is x. The second one's a little bit more cryptic. We're taking b and we're raising it to some power. But what is that number? That number is log base b of x. And so remember what this expression means. This is the power that turns b into x. So stay with me here. This is where it gets a little bit weird, but it's actually pretty straightforward if you can get past this crazy notation. We all agree that this is the power that turns b into x. If we raise b to this power, we'll get x. But that's exactly what we're doing. We're taking b and we're raising it to the power that turns b into x. So if we take b and raise it to this magic power, it's supposed to turn it into x. So these are cancellation laws. And what this actually means, and you might note here, for number 1, if f of x is equal to b to the x and g of x is equal to log base b of x, then g of f of x, which is log base b of b to the x, equals x in all cases. But this is the definition of inverses. So if f of x equals b to the x, then f inverse is log base b to the x. Which means that if I know how to graph e to the x for b greater than 1, which is this exponential growth function, b to the x, and has this horizontal asymptote of y equals 0, and this goes through 0, 1, and somewhere up here is 1 comma b, I know how to find the inverse of that function. So first of all, as we talked about in the inverse section, it is a reflection about the line y equals x. And if that's a role reversal of ordered pairs, that is to say, if this goes through 0, 1, then the inverse will go through 1, 0. And if this goes through 1b, this will go through b1, wherever that is. And if this was y equals 0, then if we switch the roles of x and y, we get x equals 0 as our asymptote, and this is the mirror image. It looks like this. and this is log base b of x. And it has some properties, right? It has no y-intercept because its inverse had no x-intercept. This has a vertical asymptote of x equals 0. It goes through the points 1, 0, b comma 1. It is always increasing. It's got a domain of 0 to infinity. It's got a range of all real numbers. You'll notice that that's flip-flopped from the exponential curve that we talked about earlier today. Its end behavior is, as x approaches infinity, log base b of x approaches infinity. But, and this is a little bit different, as x approaches, x doesn't actually approach negative infinity. Note that there's, for the blue curve, there's nothing going on over here. This is no curve here in this region. So x isn't going to go to negative infinity. In fact, if you look at this from right to left, x gets close to 0 but never reaches 0, much like the cricket in the shoebox never reaches the other side of the shoebox. And in this case, log base b of x approaches negative infinity. And those are the properties of log base b, provided b is greater than 1. Now, there's another version of this. I guess the key to what I was talking about down here was the fact that these were inverses. That's what kick-started my ability to graph this. If this is x, and this is y, and we want to talk about f of x equal to log base b of x for b less than 1, but still greater than 0. What we get is a very similar curve. So let's start off again with the exponential curve. This is the inverse of b to the x, where b is less than 1. So we know that that goes through 0, 1, and then 1b. And this is an exponential decay curve. Looks something like that. Has that horizontal asymptote at y equals 0. And this is going to be its mirror reflection about the line y equals x. And this curve is a little bit different. It's going to have it's still going to have a vertical asymptote of x equals 0. And it will go through the point 1, 0, and b1, although b is a lot smaller now. This is really confusing looking. This is b comma 1, and this is going to come close to this asymptote, pass through these two, and then get larger. So that those are in fact mirror images of each other about the red line. And this is log base b of x for small values of b. So there you have it. Those are the basic curves. This one has the following properties. It has no x-intercepts. It passes through 1, 0, and b comma 1. Almost all of this is the same, actually, except for a couple of things. Duplicate. Let me just bring this down here. And let's talk about what's changed. The difference here is this is no longer an increasing function. This is decreasing over its domain. It's still got the same domain. It's still got the same range, but its end behavior is a little bit different. This time as x goes to infinity, the log goes to negative infinity. And as x goes to 0 from the right side, this one gets arbitrarily large.